Hi, doing a mic check. Can you all hear me? Can you hear me? Hmm. You can Okay, all right. What problems do we have today? York, live notification. Hopefully our internet will be better. I managed to hook up our Ethernet connection, and I'm just hoping we don't crash. Okay. Hi, hope you're all doing well today. Some calculus problems. Theory. Homework. Was this 5? Part 2? An exhausting day. A lot of work. You know, no one's actually shared homework 6 with me, so it's probably just going to be homework 5. And if people want to look at homework 6 problems, they can share on the spot, and I'll try to see what I can do. No promises, though. Yeah, okay. Let's look at some problems. Huh. How is semester going? Is tests... Yeah, you should be coming to the end, right? Are finals going on right now? Or are they another week or so out? Huh. Also, let's just... I hope I'm not talking to nobody. Yeah, mic check, mic check. Can you all hear me? Hopefully. Hopefully I'm not just talking to empty air. But last we were talking, I think we were discussing a little bit about, what was that, question 2? We just discussed a tiny bit. The concept is very similar, so f is on a domain of 0 to 1, and x is the set of all x. So I like to draw my capital X's like this, almost like a Roman number. So x is all the little x in 0 to 1, such that f is continuous on 0 to x. So little x is all the right endpoints of intervals 0, x, over which f is continuous. So to do a problem like this, you just gotta look at some examples, right? Okay, so it's only over 0, 1, so if this is x and this is f of x, 0 to 1, if you have like a straight function going upwards, and then just something crazy happening like that, well, if this is your left endpoint, then this is a valid value of x, this is valid, this is valid, this is valid, right up until you get to that like endpoint. But then once you get out here, this is not valid. Yeah, so these are all valid, these are not valid. So if, say, this value right here is like 0.6 or something, then capital X in this particular example is equal to from 0 to 0.6. Like, it's all the right endpoints over which f is continuous. Yeah? Hopefully that makes sense. Does that make sense, people? So that's the concept, whereas the problem is kind of asking you to come up with a counterexample. So with this definition of little x and big X, they're asking for a case where S is the supremum of big X. Then, so you're trying to come up with a case where S is the supremum and F is not continuous at S. So, I don't know. Play around with a couple of examples. So like, for this particular example, right? Where it's going up to 0.6, I would say that the value of S in here, for this particular example, is equal to 0.6. Right? I don't know. Play around with a couple of examples. Throw in some jump discontinuities right there. And see if you can get a situation where... I don't want to give too much away, right? Play around a little bit. So for this particular problem, right, the supremum value of... Yeah, I might misunderstand this problem. It almost seems a little too easy. F is a function with domain 0, 1. X is the set of all little x such that F is continuous on that interval. Right? So you get to choose F, you get to choose your function F, and try to throw in some points of discontinuity and see if you can get a situation where the assertion is false. S is the supremum of capital X, then F is continuous. Yeah, maybe just to finish this off, maybe try to do a simpler example, right? Maybe just try to do a straight line going from 0 to 1. For this particular example, okay, the left endpoint is 0, and all the right endpoints are okay, because the straight line is continuous over every single one of these intervals. So for this particular one, S is equal to 1. And unfortunately, this fails to be a counterexample, because the function is nice and continuous at this endpoint 1. So think around a little bit, play around with it, and see if you can... Yeah. I mean, in my opinion, the question... You know, once you understand the question, this one almost seems weirdly easy. Yeah. If F is a function with domain 0, 1, you see what I'm saying? Yeah. I mean, unless I'm severely misunderstanding something about what it's asking, it really does feel like there's a lot of options here. Just play around with some discontinuities and see what you get. X is the set of all x such that F is... Like, I keep rereading this because I feel like I must be misunderstanding it, but it really does not feel like it's asking for a particularly complicated counterexample. Yeah? I mean, I think the idea here is to try to introduce the idea of a supremum, right? A supremum is not exactly the same thing as a max, right? That's critical that you understand that the supremum is similar, but not exactly the same as a max. Because you could have a situation like... you could have a set that looks like, 0, 0.9, 0.99, 0.999, etc. So it includes, 0.999, an arbitrary number for every number of nines, and it gets arbitrarily close to 1, but it doesn't hit 1. The max does not exist for this set. So the max does not exist, but the supremum is nice. It's 1. Yeah? So the supremum, unlike the maximum, doesn't actually need to be a part of the set. Yeah, it's, let me just choose any random point in 0, 1 to be discontinuous in order to prove. It sure seems that way. Again, I'm rereading this thing just to make sure I'm not crazy. But it does seem like any time you choose a discontinuity, S is sort of going to be that first point of discontinuity, right? S is the supremum of X. Yeah. So play around with that, and hopefully, the point becomes clear. Come up with your own counterexamples and all that. But, yeah. You want to talk about question 3 next? So it's asking about a particle traveling with velocity t minus 1 at time t. So it's asking you to divide it into 4 intervals of equal length and find the minimal particle velocity. Okay. At each of these time intervals. At each. That's a little important. So, heck, what do you want to do? Just graph it, right? What does this function look like? So if it's t minus 1, help me out here. So this is just regular t minus 1, right? Y is equal to t minus 1. So the absolute value just looks like it's reflected. Does that seem right? And it's asking you to just cut it up into, so just ignore this down here. So this is now absolute value of t minus 1, right? This is just algebra 2. So at this point, they're just asking you to cut it up into however many things. What was this? 1, 2, 0.5, 1.5, and just asking you to get the minimum value. That should be pretty easy to do just from glancing at it. Any questions on this one? We're going to start the integration process. But as you work through this, you're sort of dividing it into equal length and approximating the velocity. You're going to figure out how far the particle has traveled in each time interval. So have you learned that distance is the integral of velocity? Have you learned this? And the integral is more or less being approximated right here by the area under the curve. And you're doing a very rough approximation by yeah, you're doing a very rough approximation and getting the area under the curve, approximating them with rectangles. Does this make sense? Yeah, hopefully this isn't too complicated, but it gets a tiny bit tougher. When you start to make this a little bit more abstract, or when you start to introduce more rectangles. Yeah? So okay, so yeah, you can go through and figure out the area under the curve, or approximate the area under the curve using rectangles for each of these intervals, right? So I'll let you do that on your own. I think that's not particularly complicated. They're telling you to approximate using the minimum, so use the minimum as the height of the rectangle. But now it starts to ask you about dividing this up into 2k intervals, right? That's a little tougher, because now instead of just in nice 4 intervals that you can, like, any like 8th grader could go through and calculate the areas of those rectangles, it's a tiny bit tougher with 2k intervals, right? So this is basically, k is arbitrary, so this could be an arbitrary number of intervals. Right, so if k was like, I don't know, 5 or something, it would look like this. 1, 2, 3, 4, 5, 2, 3, 4, something like that. Yeah. And the idea here is, again, you're going to find the minimal velocity of the particle on each of these intervals. And to do that, it looks to me like, well, okay, for the first interval, it looks like the right endpoint and the right endpoint and the right endpoint and the right endpoint, and again. But then for the next batch, because it's going in the other direction, it's sort of the left endpoint of each interval, right? So you basically need to come up with a general way to express well, it shouldn't be too hard, right? These values are sort of descending in a regular, the number of steps is k, and the amount that it's declining each time should be expressible in terms of k, right? So figure out what the height of each of these intervals is, and multiply it by the length, which I think is just 1 over k. Something like that, right? Is this complicated? Is this still making sense? How are you feeling? I'm not exactly sure how complicated this is because it technically doesn't involve anything beyond like middle school algebra. I think I'm on question 4 right now. It's the one with arbitrary k intervals. I mean, they're very similar, right? Question 3 is using just preset 4 intervals, and the next one is doing a custom amount or any arbitrary amount, because the idea is you can take k to the limit to get an idea of an integral. So it's technically all like stuff you've learned in Algebra 1 or Algebra 2. It might just be a tiny bit more involved, right? I'm not even going to use the word complicated, just involved. But you really should be able to just express, for 4a, the minimal velocity depends on the interval, right? So just find the minimal velocity of the particle at each of these intervals. So I would probably say like the ith interval is expressed in terms of, the way I would do it, thinking almost like a computer programmer, I would probably vary some like step, I from 0 to like 2k, or maybe 2k minus 1. Think it through, right? Think it through. Or maybe 1 to 2k or 0 to 2k minus 1, something like that, yeah? Just make sure to get your off by 1. Make sure to think carefully about off by 1 errors. But express each of the heights in terms of I, and you should be golden, right? So then the next part B, is asking, okay, you've divided it into 2k. You've approximate the velocity of the particle. So yeah, at that point, when you've already approximated the velocities or the height of each interval, and after that, the distance in each interval is just the width of the rectangle times the height. In other words, the approximation for the distance traveled in each interval is the area of the rectangle, right? And that shouldn't be hard at all. You already calculated the height, so just multiply by the width of the rectangle, which is, what, 1 over k? Yeah? So the height is some expression, depending on the interval. And you can use a counter variable like I or C or, whatever variable you like. But I think the width is just going to be 1 over k, right? Because there's 2k intervals, and the total length is 2, so width of 1 over k. So just multiply together to get the area, right? Technically not complicated. You're just doing things, you're like kind of reframing middle school math in terms of arbitrary variables, right? Maybe even elementary school math. It's not necessarily to say that it's very easy. It's that it looks probably more complicated than it perhaps actually is, right? Integration is ultimately adding up a lot of rectangles. Feeling good so far? I'm asking because a lot of people mentioned question 4 was the other complicated problem on the set. And I get that it appears a little bit scary, but I ultimately think it's maybe not quite that bad. I hope not anyways. But yeah. Okay, so then when we know the area of each rectangle for part B, then for part C, you just add them all up. Probably use a summation notation or something like that. You might get a really nice expression, you might not. Just simplify it as far as you can. And then question 4D is basically taking the limit of that. So yeah, I probably can't, I can't do this all out without giving it away too much. But I hope this kind of walkthrough gives you an idea of what you're expected to do. Each individual step isn't so bad, right? It can just seem kind of intimidating when viewed from a distance. Yeah, so D is taking the limit as k goes to infinity. And then E is doing, imagine doing the exact same thing, but with 2k plus 1 instead of 2k intervals. And I think that's reasonably interesting, because you get that when you're doing something nice and symmetric like this, it feels a little bit more natural to use 2k, because it divides each of these things kind of symmetrically and meets right in the middle, right? If you were doing this with 2k plus 1, an odd number of intervals, it would look just a little bit funky, where the middle, the value right here is being, how do you put it? The value right here is contained within one interval, so like this right here is one interval, whereas these were separate intervals, right? But that's just a tiny bit of error that goes away as you take the limit, right? So try to argue that through. Think about how this tiny, tiny bit of, think about how they're basically the exact same thing, really. You might get a little bit more error one way than the other, but try to argue that all that error goes away in the limit. Do you get what I mean by error? When I say error, I mean the difference between the actual area under the curve, compared to the approximation of the rectangles. And for this particular problem, the area under the curve is super easy to find, right? This is maybe your hint or sanity check, is that as you take the limit, the rectangles should approximate the area under the curve. And the area under the curve isn't that complicated at all, right? It's just two rectangles. Any elementary school student should be able to tell you the area under this curve just from elementary school math. So you can probably compare your answer, after taking the limits, to what you would expect the answer to be. And the reason why this is useful is because as you learn how to integrate, this gives you an idea of this method, or once you actually learn how to integrate, it allows you to take the area under the curve of much more complex shapes. Like, for example, if you were asked for the area under the curve of a parabola, a middle schooler or a high schooler probably couldn't do this, right? You would need a little bit of calculus, because this curve actually has some, roundness to it, yeah? But for situations where it's a nice straight line, or two nice straight lines, your answer probably should look like the, areas of the triangles. How are you all feeling? Still pretty reasonable, I hope? Nothing too complicated? Are we okay to keep going, or do we have questions? What's, yeah. Anything in particular? Okay. Do we want to look at the remainder of the set, or are you all feeling good? Most people are just telling me question 1 and question 4 is what they had trouble with. Keep going. All right. So for the next one, if f of s looks like something like -2 to s, 1 minus x squared. Is this a cube root, dx? The idea here is if this is the main function, and this is the integrand, right? The integrand is basically the derivative of f of s. Yeah? So the idea here is if you're graphing this from the period of -2 to +2, right? Well, it's pretty clear that at -2, if I'm not mistaken, at -2, f of s has got to be 0, right? Because anything integrated from, the area under the curve from -2 to -2, well, that's just no area under the curve at all. That's 0. But the idea here is basically, if this is your derivative, you can basically approximate, you can basically guess the value of the derivative at a couple of different intervals. Like, I don't know, maybe guess it at 4, 5, 6 different intervals around here, and figure out the points where it's positive. Yeah, figure out the points where it's positive. And figure out the points where it's negative, and yeah, try to look at inflection points and stuff like that. Do you get what I mean? You can basically approximate what the derivative is by just plugging in values of x into here, and that should more or less tell you your slope. Right? That should more or less tell you your slope at any given point. And that should tell you how fast to increase or decrease your point. So the idea is, if you have a tiny positive derivative out here, you start off, tiny and positive for a little while. But if the derivative gets much larger, much more positive and large, then the next segment, you go up by a lot. That's the idea. You're just being asked for a rough sketch. It's nothing crazy. Someone sent out something but retracted a message? Okay. Yeah. It's, questions like these, a rough sketch is basically all you can do, right? Okay, the last one I have no idea because I don't know what definition they're talking about. What definition are they talking about? I don't have the textbook in front of me, so I don't know. Do you want to look at this one, or is this too easy to be to bother yourself over? Yeah. Now that you're getting to the end of the class, did you enjoy the class? Do you feel like you learned a lot? I feel like I have some misgivings about introducing, epsilon delta proofs to people learning calculus for the first time, because, it feels like you didn't learn much about the, applications of calculus. Focusing too heavily on theory is not how I would teach it. No. 5.2.2. Someone's saying about concavity. Concavity. What's going on with concavity? So concavity is the point when so concavity is when slope goes from So concavity, or inflection point, is when slope looks like 0 over here, and it's, positive over there, and, yeah. Hang on. Let me remind myself. Yeah, so what is an inflection point? It looks something like that, right? Where the slope is temporarily 0. And, it's positive on one side and positive on the other, but it's 0 temporarily. Do you need to look at second derivatives even? Is this sufficient to prove that it's a concav? Is this sufficient to prove that it's an inflection point? I don't know. Are there even any inflection points here? If you really wanted to, so you're given the derivative, right? The cube root of 1 minus x squared. You could take the derivative of that if you wanted to do some second derivative tests, right? Because the second derivative test at the critical point is undefined. Okay, interesting. First derivative test? Okay, sure. People aren't taking the continuation of this theory-based class? Yeah, I guess I don't blame you. I was happy to do sessions with the applied calculus class, but after the first session, I don't think anyone really expressed interest. How do you do a cube root in Desmos? 1 minus x squared? Yeah. Anyways, for the next semester, are people continuing, or? So, it looks like little f of s looks something like an omega sign, I guess? Looks kind of like that. Yeah, I think that should be enough to tell you what you need to know, right? It's like positive, positive, positive. Negative, negative, negative. Does that seem right? Yeah. So why don't you all think that through and see if you can, yeah, see if you can make some sense of that. I think it's a shame. This course probably introduced the epsilon delta proofs way too strong at the start, I think. And I wish they eased you in a little bit more. I don't even know what theory-based Calc 2 looks like. I don't know how it's particularly different from Calc 1. Is it all required for CS majors? A year of calculus? Anyways, I think we're pretty much done. I guess there is question 6, and it's talking about continuity playing an important role in a definition. But I don't have that definition. Does anyone care? What is that definition? Is that definition this sum-looking thing? Yeah. Suppose that f is continuous, then each subinterval takes on a maximum value and a minimum value. Someone sending it over on Is it talking about that sum thing? The upper value and the lower sums? Sorry, the upper sum, the lower sum? Because I mean, the definition would still work fine if it's not continuous. I'm not sure if I'm looking at the right thing here. Okay. Yeah, this is very odd. Okay, so it's just talking about the upper sum, m1 x1 m2 x2 plus mn xn. I don't know, the question is a little bit weird because, I mean, you can totally define whatever you want, right? P is a partition. Suppose f is continuous, then on each interval, the function f takes a value m and a maximum value. I mean, I guess you could just be really stupid about this and say that, I don't know, if it's not continuous, you could just have absurd situations where it keeps, like, diverging, right? In which case, like, maximum and minimums wouldn't even be defined. Yeah? Yeah, no, I guess that kind of makes sense. The definition just wouldn't... The definition would just be invalid if if it wasn't continuous and you could partition it up into a couple pieces that were just exploding, your M1s, M2s, and whatnot would start to look kind of silly. Yeah. maybe that's the idea here. As for a specific theorem from a text, I think you'll have to find that part yourself. But I don't know. Think about if you have a function that's guaranteed to be continuous, and it's on some and it's on some small interval. Think about why that could never. Sorry, how do you put it? Sorry, I guess if you know that the function is continuous on some. Yeah, which theorem would this be? The intuition should be very clear, in that there's just no way for it to blow up, because if it's got to be continuous over this entire period, right, there's no way that it could just blow up somewhere in the middle. And that guarantees that your partition still makes sense because there's maximum and minimum values. As for trying to find a theorem from the textbook, I don't know, maybe do a little bit of digging. See if there are any theorems that guarantee the existence of maximum or minimum values. But, yeah, look at that a little bit and think about how if continuous was being replaced by increasing or decreasing, why would this still work? Well, I guess one of the ideas here is if this thing blows up to infinity, right? And then it comes back down somewhere over here, right? It's no longer increasing. You can't say that it's increasing over the whole interval. So, does that make sense? Basically, the idea is that if the function over, some interval was just increasing the entire time, then there's no way for it to, blow all the way up to infinity within some interval, because it's got to come back down from the next one, right? And it's not allowed to come back down, because it's increasing the entire time. Does that make sense, or am I speaking Greek here to you all? What do you think? Make sense or not? 0 to 10, how are you feeling? Make sense? Yeah, anyways, that's the intuition. You can literally just draw a picture and think about it. But you got to talk a little bit about why. You got to think through it on your own, figure out exactly how to make, what theorem to cite, how to make this rigorous. All I've done is sort of draw a picture. Yeah, I'm not entirely clear off the top of my head which theorem I would cite. I think I would have to pour through the textbook a little bit. Okay, how are we feeling? Is that all you want to cover? I don't think anyone sent me homework 6 yet. For question 4D, should the infinite limit of the summation expression in 4C be 0 or 1? Good question. 4D, take the limit of the approximations in question 4C as k approaches infinity to calculate how far the particle has traveled between time. Okay, let's see. For question 4D, should the infinite limit of the summation expression in 4C be... What do you mean? Should the infinite limit of the... Are you basically asking if the infinite... if the sum should be 0 or 1? Well, let me draw a picture, and I'll ask you which one seems more plausible. The idea is that as these rectangles get more and more fine, right, they start to look a lot more like the area of the triangle, right? And let me ask you, does the area of the triangle seem closer to 0 or 1? Does the area of the triangle, or I guess the two triangles here, the area seem closer to 0 or 1? Because keep in mind, that's what this limit is doing, right? It's approximating the area of the triangles. And that precision becomes exact in the limit. So someone else is saying a little bit. 7. Is there a question 7 on this set? What the heck? I don't think someone shared that with me. Oh, is it that fundamental theorem of calculus question? Is it the question where, like this? Right? So f of s they define as equaling the integral. Yeah? So they're basically asking you what f prime of 0 is. And to do that, you first want to calculate f prime of s. Right? You just want to first calculate the derivative generally before plugging it in. So that's basically taking this thing and taking the derivative. Yeah? So the left-hand side is the derivative of f. The right-hand side is going to turn into a derivative of an integral. Yeah? And look at the fundamental theorem of calculus to tell you what happens when you take the derivative of an integral. What happens? What happens? You're asking an incredible question. It seems closer to 1, but if you have infinite intervals, then technically isn't the area of each interval really close to 0? It's a great question, right? Well, it doesn't totally cancel out, but this is the whole point of integration. Yeah? The idea is that, okay, if you have an infinite number of infinitesimally small rectangles, and you're adding them all up together, what is the answer? 0? Is the answer infinity? Or is the answer something in between? And at least for this particular integral, the answer is something in between. Because, like, just think about the process of taking the limit, right? If you drew, like, 2 really crude rectangles, the area is, like, non-zero, right? And then if you drew, like, 4 rectangles, so, like, 1, 2, 3, 4, well, the area is still non-zero, and in fact quite finite. It should be, very close to the area of the triangle itself. And as you're drawing more and more of these rectangles, yeah, it's the area is nowhere near 0. In fact, the area should be getting closer and closer to the area of the rectangle themselves. Okay. This question is past due? What do you mean? Wait, is the due date already done? Huh. So it's a really great question, and something that I think almost every calculus student wonders at some point. Like, God, these infinitesimally small areas, if you add them all together, shouldn't you just get 0? And the answer is perhaps not. If you have infinitely many of them, you really need to just think about the limit. Right? Think about the limit. Each one of these values should have an area close to the triangles, right? It's close to the triangles, and close to the triangles, and it's nowhere near 0. Like, I'm sure that if you did this question out, you would see that, like, if you actually tried to mechanically calculate the areas for a couple of finer and finer partitions, you would see that the value comes closer and closer to some finite non-zero number. It's a great question, though. It's very instructive, and I'm happy you asked. All right, folks. So yeah, how was this semester? This whole thing was just a spur-of-the-moment experiment. I was just helping random people with their question, and I think one student came in and was struggling with those epsilon delta problems, and eventually we invited the whole class. I hope it was instructive for you all. It was pretty fun for me. I don't have as much time anymore because work is picking back up, but I will try to hold a session here and there next semester based on what people want. Yeah, it seems like a cool idea, but unfortunately, I couldn't find that level of traction with other classes. I thought it was really cool. The first weekend when I connected with the class, something like 300 people tuned into the sessions, and I think we helped a lot of people. Unfortunately, a lot of people still dropped. Um, I kind of feel like there was a bit of a teaching failure in the class if 400 students took it and 300 dropped. But quite a few people told me I made a difference, and I think that's pretty cool. Am I a teacher? Nope, just a software engineer. I do this for fun because I miss math. Miss math a lot. Yeah. Hopefully we'll apply for a master's soon and, get some more math in my life. But, yeah, it's a way to reconnect a little bit, and I think it's a lot of fun. What else? Yeah, so stick around to my server. If you have further math classes, you can feel free to ask questions on the Math Help Discord. On my VTutor Live Discord, and invite your friends, invite your classmates. If a couple of people are interested in the same class, I'm happy to schedule a session here and there, like this one. Have I used any of this math in a software engineering job? I mean, what do you call it? You don't get to use too much calculus. My software engineering job is, more industry software code than it is any particularly involved math stuff. Maybe if I lean towards a data science role in the future, there might be more intensive math material. But no, I would say my work so far has been pretty, run-of-the-mill industry stuff. It's, yeah. Maybe as I get more experience, they'll allow me closer to do more interesting work. But we'll see. Yeah. I don't... Are most of you planning on switching to the other calculus course if you go onwards? I assume that there is an applied and a theory Calc 2. No, I don't blame you, because I think learning calculus the first time on a theory-based approach is a bit overkill. In fact, it's a little bit surprising why they recommended everybody sign up for this course in the first place. I find that a little bit, maybe it's not the right move. If it were me, I would probably teach people calculus in applied fashion in their first time through, and if they indicate more interest in math, to go back and fill in the proof-based rigor. Yeah, but if you like it, stick with it. If you don't, and you just need to get the requirement out of the way, I think the real advice is probably just go to applied calc. But I hope I've conveyed a little bit of enjoyment, or maybe demonstrated a little bit of why some stuff can be cool sometimes. You can sometimes get neat results. Oh, wait a minute. There was a part 2 to that question, wasn't there? There was a part 2 to that question. Right. I'd almost forgotten. So yeah, for the first part, use the fundamental theorem of calculus and see how that gets you. But for the second part, if you need to show that the limit of 0 of f of s is equal to f of 0, well, draw a picture of this, right? This looks kind of like a sine curve that gets bounded by a double-sided parabola. Yeah? That's what that looks like. And the idea here is how do you put it? So where does it start at? It starts at -1. Yeah, the integral starts at -1. So let's say that's over here. And the idea is that, let's say s is approaching 0. So you can say that it's approaching from the right. The logic from the left is exactly the same. But you're basically saying that the area under the curve from like these squiggles over here, right? How do you put it? So the integral of d of s from -1 to 0, in this particular case, is equal to the integral of d of s from s -1 to s is equal to negative 1 to 0 plus 0 to negative 1. Right? And I think the idea is that you just need to look at the limit. Yeah? Basically, minus d of s, 0 to negative 1, so this is an integral, to 0, negative 1, d of s. So this is, this side doesn't require a limit at all, right? It's just a straight up number. But the idea here is if you take the limit of both of these pieces, you can kind of try to prove to yourself that this piece goes away to 0 as s goes to 0. Oh, did I write this wrong? This should have been... Oh, this is stupid. This should have been from 0 to s. Yeah, because this is basically saying... Oh my goodness, I'm just running all over the place. This is basically saying if you add up all the area under the curve and overshoot 0 by a little bit, and you go back and subtract this part out, that's equal to the area under the curve from negative 1 to 0. And this is basically saying if you just try to show that the part that you overshoot goes to 0. The area that you overshoot by goes to 0 as you move back to the origin. Hopefully that makes sense. And the logic from the left side is pretty similar. You can just... Yeah, I think that's how I'd think about it. And remember, there's a rule here that, if AB plus BC, so the integral of something from A to B and B to C is equal to the integral from, I think, A to C. Right? The integral from A to C. And this kind of makes sense when you think about it, area under the curve, right? It's basically like saying if you have some function that, has a point A and a point B and a point C, this is basically saying that the area under the curve from A to B plus from B to C is the area under the curve from A to C. And visually, that should make total sense, I hope. That's, essentially why this works. And hopefully you can use that fact for your problem to show you that the amount that you overshoot or undershoot by goes to 0 as the limit as s approaches 0. Make sense? Any other questions? Yeah. If you folks have extra questions for me next semester, feel free to go ahead and ask. You can feel free to ping me on the VTutor Live Discord server. Happy to answer questions and help students out. Help you learn your math. Yeah, number 1 we did on a previous stream from, I think, Saturday. So perhaps go check that one out. Number 1 is the most involved set. Number 1 is probably the most involved problem. So go check that out. Yeah. All right, folks. Well, take care. It was a fun semester. And see you around. Oh, and if you all stick around, sorry to be annoying, but please do like and subscribe to this channel. I've noticed that a lot of students have not been aware that we've moved over from Twitch to YouTube, and also don't seem to be aware of when I go online. So subscribe, and you'll probably get notifications. I think that's how it works. All right, folks. Take care and good evening. Back to work. This was a fun semester.